Good morning, and I hope you all had a wonderful winter break. Unfortunately, because of the 2-hour delay, my schedule got messed up and I can't be here with you, but I've got a video that hopefully will be almost as good. So let's get started. So hopefully what you're looking at here is some things that you remember, at least a little bit from before break. We're going to review all of them in a minute, but these are some of the things we learned, proved, kind of discovered before break, and we're going to now put it all together to um, solve complex circuits. So starting out, we had the loop rule. Um, and the loop rule is over any closed loop through a circuit, the net voltage change must be zero. Okay, and we'll do some examples of that in a second, but that's the idea, right? That if I end up where I started, the total change of my voltage has to be zero because the voltage of that I'm starting and ending at the same place. And so the voltage must be zero at the beginning and end. Okay. Charge conservation, charge can't be neither created or destroyed. That means any part of the battery that's isolated from any part of the circuit that's isolated from the battery. The battery can provide extra electrons or it can absorb extra electrons. And it must have a constant X charge. Today, that will be zero. Um, so we will do problems where the circuit starts out partially charged, but for today, it's going to start out all neutral. Okay? Equivalent capacitance means it's just like if you were to replace a pair or more of capacitors with a single capacitor, what would that equivalent capacitor need to be to get the same charge from the battery? Okay. Um, and finally, we have Q equals V times C. Remember that really that Q is the absolute value of the charge on one of the sides of the capacitor, right? Because the capacitor is going to have positive and negative on the two sides. And then the voltage, right? That's the difference in voltage on two sides. So it's not an absolute voltage; it's the change in voltage. Of course, the C is capacitance. All right, so let's run through a little loop rule review here. So here's like a fair capacitor setup. About that. They changed some settings on the PowerPoint here, but good. Hope. Here we go. All right, so you typically want to include the battery, but not always. So we'll do all the loops possible here. Our first loop, okay, and a loop. So let's go this way. All right. This is the lower end of the battery, and this is the upper end of the battery. So if we wanted to, this change in voltage over the battery, right, is positive. I'm going from the small end to the big end. So I've got 0 equals this. Now that is a symbol that typically refers to the voltage change of a battery. All right. Um, don't worry too much about, lost my cursor. There it is. Don't worry too much about what it means right now. It has a specific name, but that can be also just used as the voltage of the battery. All right. Then we go to our first capacitor. And our capacitor here, this is the positive end of the battery. So this is going to be the positive end of that capacitor, which means the other side is going to be negative, right? So I go from positive to negative. That's a decrease in voltage. So it would be minus V1. All right. And then here we go again. This is the negative side of that capacitor. That's going to connect to the positive side of this capacitor. Negative side there. And we go from positive to negative, again in our direction. So it'd be minus V2. Okay. The second one we could add, the second loop draw, loop that goes from here, right, through C3 instead. Again, same direction. Again, we would start with 0 equals the EMF. Okay, we're going through V1 again, positive, negative, so minus V1, and then again it will be, oops, we have a positive, negative here, it's V3. There's a third loop we can draw here, and that third loop is going to be the one that goes through this loop here. And again, we have to give it a direction. I always go clockwise. It's not necessary. Like that doesn't matter. Anyways, this one is 0, and we go from the negative end of C2 to positive end of C2. So that's V2 is positive minus V3. Okay, those are our 3 loop rules. All right. Charge conservation is our next step here. Charge conservation, right, is looking for parts that are not connected to the battery. Is one section of this um, circuit that is not connected to the battery, and it's this right here. Okay, and we know, as we talked about in the last slide, that this is the negative side of C1, the positive side of C2, the positive side of C3. Okay, the charge on those 3 sides, this isolated piece of the battery, must add up to 0. So I've got 0, that's what it started with, the charge, equals the negative Q1, so negative Q1 plus Q2 plus Q3. And that's our charge conservation equation. Equivalent resistance review, okay? We're looking for capacitors that are in series and in parallel. And if you remember, the definition of series is that a loop that goes through the battery, if there's only one battery. If there's more than one battery, we are in a whole different situation. Don't worry about that yet. One battery, a loop that goes through the battery, that goes through one of the capacitors, so let's go from the battery to C1. All right, if it goes through C1, it must go through the next capacitor. It has to, okay? And in this case, there's no path where I have to go through C1 or C2 or C3. I have the choice, okay? Instead, we have capacitors that are in parallel, because parallel is you have the choice, you starting here, you have the choice between this point and this point. I can either go through C2 or I can go through C3. All right, and because I have that choice, all right, and they start, a pathway starts together and then comes back together only going through those capacitors, we can say C2 and C3 are in parallel. And so, if we wanted to find that, the equivalent capacitance, which I would usually call C23, for parallel, remember for parallel it's C2 plus C3, or in this case, 0.125. All right, and then, all right, now we have a circuit, right? So the whole idea is I've combined C2 and C3. So now my circuit looks like this. Where this is C1 and this is C2, 3. And now any path that goes through my battery and goes through C1 has to go through C2, 3. So C2 and 3 are in series. So let me write that up here. So C2, 3 parallel. And then C1 and C2, 3 are in series. So I would do 1 over C 1, 2, 3, or you'll see sometimes this is just called C equivalent because it's like the total or C total, but it doesn't matter. Equals 1 over C1 plus 1 over C2, 3. All right, and when you solve this out, we get C1, 2, 3 is going to be equal to 0.0556. And if you're ever worried about whether you've done the math right for this, in series, so C1 was 0.1 and C2, 3 was 0.125, okay? Your equivalent capacitance is always going to have to be less than either of them in series. So, works out. Okay? All right. Now let's talk about how we put it all together to solve a circuit. There are 2 methods. One I think I showed you right before break, you might remember, which is to take all of your loop rules, your charge capacitance equation or charge conservation equations, and then Q equals C times V, and solve them as a system of equations. And that works for situations with up to 3 capacitors. It's also always true. So there'll be situations where we have to use that. But when you have more complicated circuits, it's usually easier to use equivalent capacitance at some stage. So that's what we're going to go through here. And this is the way I want you to kind of think about it. Um, so when I solve a problem, a complex circuit with one battery, I'm going to first go through and predict the positive and negative sides of each capacitor. Should be relatively easy. I'm going to set up a table, and you'll see what I mean by that. The table is just an organizing tool. It's not like actually required. And then we're going to use loop rule, charge conservation, Q equals V times C, or equivalent capacitance to solve for something. And you're going to repeat until the circuit is solved, okay, which means I've identified the charge, the voltage, and the capacitance of every piece in that puzzle, okay? Now, in group 3, you typically are going to have to, the hard part is identifying which of those rules you're going to use next. Okay, think of this kind of like Sudoku, right? Where Sudoku, there's like a bunch of different rules. You can't have 2 of the same number in the same row or column, but you also have to have 1 of every number in every row and every column. And you can't have 2 of the same number in each square. And so you're kind of like going back and forth between each method until you get your final answer. Okay, so let's see what it looks like in practice. All right, so same simple circuit here. I'm going to show you. We've got our circuit here. We've got, this is my positive side and negative side. Again, positive connected to the big side of the battery. And then once I know this is positive, this is negative, it should be pretty clear this is going to be positive, negative, positive, negative. I'm then going to create my table. All right, let's create it down here, get it out of the way here. So my table, it should have 3 columns, or maybe 4, depending on how you want to organize it. And then it should have the number of rows it should have are the number of rows of capacitors in your circuits plus 1. So I got 3 capacitors, so I have 1, 2, 3, 4, and I usually do it with 3 columns. Some people do it with 4 columns. You'll see why in a second. And I'm going to label this, okay, Q, V, and C, because quite literally, Q equals V times C. So if I look at this, I can use that equation to solve it pretty easily. And this is going to be either total, um, let's say total for now, but you could also write the battery. It's kind of, well, it's interchangeable. It makes sense in both ways for different reasons. So C1, and this is C2, and this is C3. Okay, so I can fill in what I know. Uh, EMF is basically the same as the voltage, so my total voltage for this circuit is going to be 10. Okay, and then I have C1, which is 0.1, 0.1, and 0.25. Okay, so I am looking again at my 4 rules. I can do a loop rule, a charge conservation, a Q equals V times C. Let me write them down here. Loops, charge, Q equals C times V, or V times C, I guess, which I wrote it on there, and equivalent capacitance, CEQ. And basically, I want to be doing one of these steps each time, and I want to fill out this whole grid. Q equals C times V is definitely the easiest. You can see right now there's no way I can use it for any of my rows here, and that's part of why I set it up this way, is to make it easy. When I've got a Q equals CV, I can do it easily. I clearly don't have enough charges to do charge conservation, and I don't have enough voltage to do any of my voltage loops. So the only one to do is CEQ is the most time consuming generally, but it's also oftentimes the one you're going to start with. So fortunately, we've already solved for that, right? Remember, we just did on the previous side, the CEQ for this one, we found it was 0.0556. Okay, so put that here. That's our total. Oops, point 0, point 0. Oh, can I unerase that? Eraser. All right, here we go. Fix it. 0.0556. Okay. Now, as soon as I've got that, I'm going to be like, oh, I can solve for the total charge of the capacity of the circuit. This is how much charge the battery with. So Q total equals V total times equivalent capacitance. Or you could write this is also Q battery equals the voltage of the battery times equivalent capacitance. All right, either way, we're going to get the Q of the battery is going to be 0.556. Okay, now I've just found a charge. So my instinct when I've just solved for a charge, and this is not always going to be true, is to look at charge conservation, right? Kind of want to be if I just the next thing. So the charge of my battery is 0.556 coulombs. So if I've got that, I think where did that charge come from? So that means 0.556 coulombs of negative charges left the bottom of the battery and split between these two. Doesn't tell me anything. But also 0.556 coulombs of electrons left the positive end of this and entered here. So I know that Q battery is equal to Q1. So 0.556. Immediately, hopefully you noticed here, I've got a Q equals V times C situation. So Q1 equals V1 C1, right? Which means that 0.556 equals V1 times 0.1. And that means that V1 is going to equal 5.56. Okay, I just solved for a voltage. So guess what I want to do next? Probably want to use a loop rule. Oh, remember I've got these loops, 10 minus 5.56 minus V2 is going to equal 0. Oh, so EMF minus 0 is going to equal EMF minus, or the voltage of the battery, it's called EMF, the voltage of the battery, minus minus V1 minus V2 is equal to 0. Well, I can plug in here, so that's going to be 10 minus 5.56 minus V2. V2 is going to equal 4. What was it? 4.4. Yeah, 4.44. Why did I? Okay. 4.44. Oops. And then, not surprisingly, if you remember also, that's also going to be true for V3. Okay, now I can do the last bits here, right? I can find Q. So this is going to be 0.444. This one's going to be 0.111, right? Now, you can always check when solving a circuit like this, you can always check to see if your answer is correct. Because the final thing we didn't do, so once we solve for those, the final thing we haven't solved for is we know that Q1 was supposed to equal Q2 plus Q3. Let's check. Let's see if we're right. This was going to be 0.556. Calls to check. 0.556 is equal to 0.444 plus 0.111. And it's not quite right. Obviously, it's very, very slightly off, and that's just because of rounding. But we're basically good. All right, great. So that circuit. And typically a problem, like, if you're asked to take a web design problem or some of the practice problems you do, it's going to ask like one of these pieces. And oftentimes, like trying to find just one of them, it's just easy whatever you can in the chart until you find it. All right, let's look at a more complicated one here. Oops, excuse me. Here we go, right here. So I'm going to modify this. We're going to pretend capacitor right now, equivalent capacitance, and the combined capacitance. Because that's a little bit of a complication that I don't want to deal with right the second, but that we'll deal with after we solve this and practice one with 5 resistors. All right. So again, I'm going to make my I'm going to go through and make my positive negative. This side is positive side A. That means this is going to be the negative side of A, the positive side of B, the positive side of C, the negative side of B, negative side of C, positive, negative, positive, negative. Okay. All right. So I'm going to make my chart. All right. I have 5 capacitors, which means I need 6 rows in my chart. A nice big one. Lost my, where'd my cursor go? Oop, up there. All right, we're gonna ignore that. Pretend I didn't do that. Okay, we have 1, 2, 3, 4, and then 5, 6, and it still has 3 columns. Okay. All right. So this one is going to be right. This is A, B, C, E, and F. And I know I skipped D, but again, I'm combining B and C here, and we have Q equals C times V. All right. And we go through. We got 3 4/3, 1, 2, and 6. And then we have the voltage of the whole battery is 10. All right, and we're going to start from there. Remember, we got the 4 paths, 4 options. So clearly the first one here is going to be equivalent capacitance. So first thing I'm going to do is I'm going to erase this. I'm going to start combining ones here. So let's do it here. Let's do it. So the first thing is that if I'm looking at this, the only actual, oops, lost my, oh, there it is. My only actual ones I can combine here are E and F. E and F are in parallel. So C, E, F equals 2 plus 6 or 8. Okay, and then C is in series with EF. So 1 over CEF is equal to 1 over 1 plus 1 over 8. CEF is going to be 8 over 9. Okay. Again, and that's, you notice in series it's smaller than either of the original, which is good. And then C, so that was this one here. We combine this. And then CEF is in parallel with B, so we add them together. So we got C, B, C, E, F equals 4/3 plus 8/9. And that comes out to 29ths. Okay, and then we have for C total, right? Oops, that's a, sorry, one there. Oh, I'll just keep going. C total, 1 over C total is equal to 1 over A, which is A plus 1 over CB, CEF. And when you do that, C total comes out to be 1.28. All right. Okay. Again, I'm going to erase a few things here that were mistakes just to make this a little less gross. All right. So we now have the ability, or we now can look at this and be like, okay, what's next to solve? Well, obviously, right, we have the, where's my pen? Oh, there it is. We have this spot right here to solve for, and the Q of the total is going to be 12.8. So we went C total, we had C total, and we found Q total equals 12.8. Okay, Q total, right? If we look at the circuit again, everything from the volt or everything from the battery is going to go through A. So Q total, this gives us QA equals 12.8. Um, and actually, I'm going to make a slight adjustment here because I realized I screwed this up earlier when I was practicing this problem, and it actually matters. I need one more decimal place. So let me erase these um, because it actually is going to matter in this problem whether we have one more decimal place on this. Do be careful. When I did this, the screw up wasn't so much a screw up as like a um, uh, like nothing I'm doing is wrong. Like rounding this stuff isn't wrong, but it throws off your ability to check your answer at the end because of the rounding. All right, so I've got this again. I've got QA and QC, or sorry, and CA, QA and CA. So I should be able to find VA. Okay, so this goes to um, VA, which our VA will be 4.253. Okay. Again, keeping a little extra decimals, not rounding. And you'll see I ended up, I'll tell you where I made where I realized I needed to keep an extra decimal place and had to go back and redo it. All right, so now, all right, I need to look at my options here. So I've got this far. I'm gonna look at my loop rule. I just solved for a voltage, seems like a loop rule situation. Let's go ahead and erase these circles here to give us a little more room. What if I want to do a loop rule? The three loops I would draw here are this one, right? This one that goes around the outside, and then maybe a little small one in here, um, that kind of thing. But these are with voltages. So where did I just learn some voltage? I know the voltage of A. I know the voltage of the battery. The one I can do that isolates this is let's go back to green here. Is that oops, I have a hard time finding my cursor, guys. Sorry. Is that I know that 0 equals 10 minus VA minus VB. Again, where VB and VD are combined into a single VB. All right, this is going to lead to a VB equaling 5.746. I think that's the right if you do the rounding properly. 5.746. Oops. All right, so I've got VB. Hopefully not surprised. You shouldn't be surprised here to learn that I'm going to then find QB. So QB equals, right, 4/3 times 5.746, which is going to equal 7.661. Okay, so again, let me erase a couple here. Gives us 7.661. Okay, so then we just found a charge. We probably want to use charge conservation now. So what isolated pieces do I have here? Well, I've got this little beautiful isolated piece where it's the negative side of A, the positive side of B, and the positive side of C. So what would the relationship there be? Well, it would be negative 0 equals negative QA plus QB plus QC. And look, I've got 0 equals negative 12.76 plus 7.661 plus QC. QC ends up being almost exactly 5.1. So I've got that. Again, find the voltage. Nicely, it's just 5.1. So let's just write that down. This goes to VC equals 5.1. Okay. And then we can do voltage rule again, because I've got a loop that goes through the battery, A, C, and then E, or A, C, and F. Okay. So I've got 0 equals, and I guess I should erase that. There we go. 10 minus VA minus VC minus VE. Could be VE or VF, but VE is equal to VF, and they're both equal to 0.63. Okay. Obviously, our next step now would be to find the Q's for them. So this goes to QE equals 1.26, sorry. And QF equals 3.78. And if you add those two together, we get 5.14, which is just a little bit above what QC was. So again, and that's just rounding, but we're actually pretty close here. So this is 1.26 and 3.78. So it ends up working. Okay. Final thing to note about this is that the last thing I could ask you for is to find the energy stored in any of these capacitors. And remember that the energy storage of a capacitor is U equals 1/2 Q times V. So if you solve for solve the table, you'll get it. All right. We have one more two more things to note here. Okay, so let me skip here. There are a couple bonus rules. Oops. Okay, if the circuit looks like it has two completely unrelated parts that do not interact, solve two circuits. So let me draw what that looks like. Okay. So imagine you have a battery where it's like battery, capacitor. Then also off of that you have like this whole thing. Okay. Here's the deal. Any loop that goes through, let's call this A, B, C, and D. Any loop that goes through A is unrelated to anything that goes through B, C, and D. So you would solve this as A being connected to the battery and B, C, and D being connected to the battery as two separate circuits. Okay. All right. Capacitors are in parallel. The charge distributed them will be proportional. Okay. So let's look back at the last problem here, and we'll show an example of that. So if you remember, VQC was 5.1. Okay. Now, this is our charge conservation for QC. So we have 0 equals QC, negative QC, it's the negative side, plus QE plus QF. Okay. And now we're going to proportional splitting. So F is 3 times as big as E. So QF is going to be 3 times QE, which means QF is going to have, is going to have 3/4 of QC, right? And QE is going to have 1/4 of QC. All right, this has to be true because they have the same voltage and therefore and all that stuff. But it's a nice little trick you can use to shortcut here. This would end up being 3/4 of 5.1 would end up being 3.83, and 1/4 would be 1.28. And if you remember, we checked on the previous, we ended up solving for these two being what was it? 1.26 and 3.78. So we're pretty close. And again, it's just a question of rounding. Okay. All right. If periods are in series, the total voltage over the capacitor will be distributed inversely proportional. So let's look at that again. Now this is going to be relevant for B and D. So we're separating B and D out. What I know is that B and D together, right? Because VA was 4.253, which means that if we did the loop rule, we would have 0 equals 10 minus 4.253 minus VB minus VD. So that means VB plus VD equals 5.746. Okay, right, we found that earlier. It's going to be inversely proportional, which means that VD is going to be equal to 2 times VB. All right. The reason is that they have to have the same charge, and so to move the same amount of charge off of one that's a capacitor half as big, you need twice the voltage. All right, that means VD is going to have 2/3 of this, and VB is going to have 1/3. So VB would end up being 1.92. VD would be equaling to 3.84, which are 1/3 and 2/3 of that. And this, by the way, would lead us to thinking that this had 7.68 coulombs and 7.68 coulombs, which we know is very close to the actual, which was 7.6, or what we calculated was 7.66, and it's the same for both of them. All right, you guys have 6 problems I've got to solve. Whoever is subbing for me has the answers to them and can check them off, and my phone is going off at the wrong time. So please go ahead and try and solve those. You don't need to be finished. If you don't finish all of them, that's okay. But then whenever you've got one, check it off with whoever's in there with you. All right. Have a good one. Bye.